I'm going to bring this for speakers about the speakers. He mostly investigates graph and paradox complexity using a lot of the molecular methods. So the topic of actually sense so the use of
Thank you. Can you hear me well? Thank you very much to the organizers for organizing this wonderful conference and for inviting me. So I will give an overview lecture. It will not be very technical. If you have any questions at any point, please interrupt me and ask these questions. Okay, so it's about advances in algorithmic meta theorems. What is a meta theorem? In algorithmics, we often look at long lists of problems. Yeah, we have many problems with vertex cover, dominant set, China tree, and so on and so on. What we want with these meta theorems is to have a theorem explaining the tractability of a long list of problems at once. Yeah, not for one problem, but for whole classes of problems. And I use the approach here of describing these problems by logic. Logic can very elegantly describe the problems that we are looking at. Let us look at an example. For example, we can state the dominating set problem by first order formula. What we say? We say that exist k vertices. You see these existential quantifiers in the beginning. And then for all vertices, either they belong to one of these k vertices, or they are adjacent to one of these vertices. Yeah, this is the dominating set stating that it exists a dominating set K. Or we can look at the three-colorability problem for graphs. We can use monadic second order logic here. We can state that there is a color. So with monadic second order logic, we can also quantify over sets. These are our colors. So we say there are three sets, the colors. Every vertex shall be in one of the sets. So shall receive a color. And then we say when there is an edge between two vertices, so for all x, for all y, if there is an edge, then they must not get the same color. Yeah, so this is the three-colorability problem. And so with logic, we can express many problems. And what we are looking for by Siebertz at this point, we want to say every problem we find within a certain logic is tractable. Yeah? So what is the use of such a theorem? Of course, it's a very general theorem. It gives a uniform explanation why certain problems, all of the problems in this logic are tractable. We also care for the techniques that we use. Yeah? So we distill the techniques from all of these problems in the model checking problem for the logic. And we say, this is really what it's all about. And then we have corresponding intractability results. We have the low one, we know the boundaries where the techniques can be deployed and to what extent they can be used. Yeah. So let's look at the complexity of first order model checking, where we're interested in first order logic. So I write a signal here and zero.
Yeah, we really hope this doesn't happen again. But it is CRS1103 is the password in case.
Okay, we are back. What we define now is the ordination rank of a formula. So we start with sigma zero equal to pi zero of the quantified field formulas. And now we're going to have defined pi t and sigma t. And I define sigma t plus 1 to be the set of all formulas that start with an existential quantifier block. And pi t plus 1 all the formulas that start with a universal quantifier block and then followed by sigma t formula. Yeah, so it's about the ordinations of the quantifiers. And it turns out, yeah, so let's look at an example. For example, the subgraph isomorphism problem is a sigma 1 formula, where we have a fixed pattern graph H that we are looking for in our graph. We formulate this with n vertices, with H of n vertices. We quantify whether it's an H or a non-H. This can be done by an existential formula. Yeah, so this is the sigma 1 formula. You see this problem is anti-continuous. Yeah. Then we have the formula, the dominating set formula, the existential block, and then the universal for all of them. So and it turns out that model checking for first order logic is very difficult. Yeah? So the T level T quantifier ordination, so model checking for sigma T formula is complete for the T level of the polynomial network. And model checking for first order logic is complete for T level. So there's no hope when we look at classical complexity to have a good theory of tractability. All these problems are very difficult. So maybe we can do more when we look at parameterized complexity. And parameterized complexity, we try to look in a more refined way. We don't measure the running times only with respect to the input size, but with respect to some additional parameter. And let's say as a parameter is the length of the formula. What is the parametric parameter that we define? We want to know, given structure and formula is the formula true, and the structure parameterized by the length of the formula. And here we do a refinement of those quantifier ordination hierarchies. So we let sigma t1 be the set of all sigma t formulas, where only the leading block may belong. And after that, you only have individual quantifiers. Yeah. So here, the first example, we got the sigma 1 formula, we just leading and the block has no ordination, so we cannot distinguish it. But here, only exactly that, with the long existential leading block, and then a single quantifier, making this sigma 2-1 formula. So unfortunately, also with respect to parameterized complexity, the problem is very difficult. And this model technique for sigma t1 formula captures the W. Yeah, which is higher than parameterized complexity, which is usually used to say that the problem is not fixed parameter effective. So sigma t or sigma t1 model checking is complete for the T side of this hierarchy. If we drop this condition and we just have the sigma t model checking, we probably for another famous hierarchy, the A hierarchy. So this is more general than the W hierarchy. Each WI is from AI. Again, this is completeness. We have a very hard problem. So our agenda, or let us put an example, where we have the dominating set problem, our sigma 2-1 formula, a very famous W2 complete problem. Let me show you also A two-part problem. The P-dominating set problem, for example, you can see that you cannot formulate this with a leading block of single variable, what we want. We are using graph two variables K and L, and we ask whether there are K vertices that dominate all the peaks of type L in the graph. What we need there is our dominating vertices, K quantifiers, saying that it's a dominating set 4 cities. And we also have to quantify the T's, so we need these 2 quantifiers. This is a 2 high problem. So that you can formulate sigma 3, but not sigma 1. Okay, so this was our agenda here to provide tractability for logics, and you see that we failed quite badly if we use this parameterization. So what's changing now, what we need to look at, we need to look at restricted types of inputs. We cannot get tractability on all kinds of structures, so what we want to find now is the most general classes of structures or graphs in many cases, because we have a rich structure theory for graphs, we can measure complexity of graphs. We want to find the most general graphs where the problem is still fixed parameter. And this is what we try to do. There is the very famous theorem of Purcell, who in a sense started this whole area. He provided the first algorithmic theory. He proved that every monadic second order property has the efficiently effect in linear time on every class of graphs with bounded trees. Yeah, this is from 1990, proved by Purcell. In the word parameter syntactically, we have this one here. This, yes. So we have this arbitrary dependence on the formula phi, but then a linear running time in the graph whenever the tree is bounded. For first order logic, we have a similar theory. We test first order properties in nowhere dense graphs in almost linear. We don't matter so much what these nowhere dense graphs are, just that we have heard them. We will see that they are actually something special for first order logic. Both bounded treeless and nowhere dense classes are special for monadic second order logic and for first order logic. And we will see many of these properties. So from a logical perspective, it turns out that if you have a subgraph closed class, yeah, so wherever a graph is in the class, then all its subgraphs are also in the class. Then it's not on treeless if and only if monadic second order logic cannot define all graphs from them. So it is somehow the limit of encoding everything. And obviously, like what we are defining, we make a new actualization by a formula. So we have a formula with 2 free variables, and we connect 2 vertices when they satisfy the formula. Yeah, so if you give an input graph, this formula will be the output graph. And you are at some additional colors in the very beginning. This is what's called a transaction. So whenever I say defining and new instructions, I will have the next slide. So what do we get from this? If we can encode all the graphs, then we immediately get hardness of model checking as soon as we have unbounded trees. If I can encode all the graphs, well, I can just translate. I can take an arbitrary graph problem. I translate all the graphs in my graph class as unbounded trees, and I will have hardness of model checking. So monadic second order logic is very intimately related with bounded trees graph. For the tree that MSO monadic second order logic cannot define all graphs. Only with and only given graph. The same is true for first order logic, and these nowhere ends. Yeah, so a graph is nowhere ends if and only no first order form can define all graphs from the class. So again, we immediately get hardness of model checking if the class is somewhere else, it's not nowhere else. This is for subgraph, for example, which are sparse graph classes. So for sparse graph classes, this model checking or this algorithmic theorem, this whole theory is essentially complete. We know we can have MSO on bounded treeless graphs, FO on nowhere dense graphs, and we are there. So we have the following picture. We have this hierarchy of graph classes starting with bounded treeless graph with the three widths over there, and it's only regular, and it goes for first order all the way to nowhere. But the key region of graph classes, then graph classes, where we don't know the picture and where we try to explore what's going on in this world. So our research agenda in this area is to find the most general graph classes where model checking is tractable. So let's go beyond boundary tree grid stuff. We can even have counting MSO. This is an extension of MSO. On concept we found T grids. And so T grids can be seen as a dense analog of tree grid. We have the theorem of return of the road from the economy saying that there we can still do efficient monitoring. Yeah, so the tree grid graphs. We then have the tree-like structure, but we have a dense analog of tree grids here. And these expressions can be approximated quickly, so we can actually do modeling. And it turns out that tree grids is again something special. Yeah. This is now without the extension of the subgraph folder. If it only no counting and so on. So again, from the logic point of view, there is something special about tree grid, and we get patterns of model checking, of course, because we can encode all the graphs. Okay. So efficient model checking for MSO possible here all the way up to our tree grid, and symmetry on our tree grid, we get patterns. So I decided to do this now. By saying CMSO cannot interpret everything, cannot define everything. So the logical definition of the class, I can also do a more constructive definition. I can define it on the previous graph exactly as those that can be obtained by MSO transactions from trees or from graphs from tree grids. That is equivalent. And let's see where the MSO transaction, where the MSO transaction is for first order. Yeah. So let me go into these transactions a little bit. So what would be a dense analog of planar graphs, for example? Yeah, we have tree grids, sequence, sparse graphs, dense graphs, nice analogs. What would be a dense analog of planar graphs? Maybe map graphs. Yeah, this is something related. What is a map graph? We have the map graphs as intersection graphs that connect internally this region of the receiving plane. You see it in the figure. Yeah, we have the places there, the regions. Each region represents one vertex. And then you connect two of these vertices between them whenever they share the point. So they are planar graphs, but we can have an intersection point of many regions in a column. If you see it in the middle, we will have many points meeting for many regions meeting at one point. So we can have very dense map graphs, as opposed to planar graphs, which are very sparse. And a different implication is map graphs are half spares of planar bifurcations. If you make one point for each region and one point for each of the intersection points, and you connect them in this way, and you see the figure here, we have the blue points representing places, and then the red point for the you connect the blue points when they have two. But we throw away half of the vertices. And this is a special case of such a logical transformation of such a transaction. We put some colors on the vertices, we have blue and red vertices, and then the formula telling us which edges should be there. Yeah? Connecting blue vertices when they are distance 2 in this graph. And this principle we can generalize. We will always construct new graphs by first coloring the vertices, then defining the new edge relation by a formula. Right? So we give a formula named in your edge. If your vertex is blue, your vertex is what blue, and the difference between blue, you decide on this formula. But on the logic, we say that you need the red vertex connected. So this will be fine from this representation of map graphs. And this representation here on the right, you will define a map graph with a transaction. And then in the end, you can take it into subgraph, throw away your red vertices. So this is a logical transaction, and it has a general setup exactly like this. We will transform the graph H into a new graph G by always adding those colors, then doing our interpretation, getting the new edge relation, and finally taking the new subgraph. So this will allow us to go from the sparse world to the dense world. whenever we have a star, so one vertex with many neighbors, and we take the second power, we will get something very nice. So this is a way to lift from the sparse world that we know, the left line here as the graph classes, we can go to sparse. So we have the limits of overactivity to know that there's graphs. And for subgraph classes, we were down here, the classification is complete. We cannot go, we don't know that there are examples. And now looking at the theorem that we have for CNSO, yeah, we had tractability when we couldn't define all graphs from all class. We want to project the same for first order logic. So let's make a class of the so reduced subgraph now. And we conjecture that modification, first order modification, would be on this, no formula can define all graphs. Yeah, very natural conjecture. And as you can imagine, this is something that has been studied in model theory. In classical model theory, people care about first order logic, they look exactly this. Yeah, so there's a very rich theory on such classes that cannot define everything. These are the values classes in model theory. This is the name. These are the so-called monadically dependent or NLP structures. Now, this whole theory was developed, started to be developed in the classification program of Schiller. He introduced the patient dependence in model theory. This for infinite graphs in classical model theory. And what we try to do now is to get a combinatorial theory for finite graphs and ultimately get model theory. This is our motivation to study these dependent graph classes. But of course, there's a lot more to discover, which combinatorial structure. So this is when the monadically and P class is set on top of everything. Everything we have seen so far is monadically. And we conjecture that we can do first order modification all the way up to those countries. Now, what do it mean? What are examples of these classes? Let us look at this concept of transduction model. So let us call that a class of structures has a property P. And we want to lift this via construction. So we say that the class has structurally P, if it can be defined from a class with a property P. So planar graphs, macro are structurally planar because they are opaque as a construction of planar graphs. So it seems very reasonable that if you have a class that has structurally some properties, you will be able to recover the underlying graph class with the properties that are interested in. You can find the model checking there, and lift the result for the class with the structural properties. And this was the hope that we had when we looked at this and so this was done first in 2015 by Dariansky and others. We looked at very, very simple graph classes with structurally bounded degree. So if you have bounded degree, this is very, very simple. If you move a construction, you can have large degrees of course, but you will not have many degrees for it. Yeah, because things will look like locally everything looks very similar, even though you come to there. What we do is that it really lift the model checking. I will observe you in the model checking on classes and the structurally bounded degrees. This was lifted, classes with structurally bounded expansion, an important subclass of knowingness classes that we have seen before, and we could very easily lift this to classes that are structurally knowingness. So this method really works, lift from the sparse base class that we have. If we go by transduction to something dense, we can actually recover some of the methods and lift the very size. Yeah, so this is how the picture is now. We have the sparse class on the left, and we can extend model checking to the dense analogs. Let us look at how we do this model checking. Yeah, so what is the method? How do we do model checking? Let's get some idea. For the very basic idea is based on on the function theorem for first order logic, diamond's totality theorem, that says that first order logic can express only local effects. So every first order formula can be rewritten as a Boolean combination of local formulas. That means we will also look at some radius r ball in the graph, and we need to check not locally what's going on, but only locally graph the three variables. And then also send this form, what we take is that you have S variables, S vertices, and then you locally set times the ultimate. And then you say these must be far away. So pairwise they must be distant greater than 2 hours. Meaning nothing else that the R balls are distant. So again, you locally test for all the vertices, do that with local property, and then I'm looking for an independent set, therefore for local balls that are distant. Looks like a completely local property, right? If you look for something that is far away, but I really, if it's also something local, well, you really look for the vertices satisfying this property. Either you succeed by finding your S vertices, if not, all the other vertices that have the property must be close to one of the vertices that define this algorithm. So all of those words again. So it's a purely local property that you have to check and verify. For all the vertices, locally test the properties, and then solve this part independent set problem. And this is a model algorithm. Because the transformation into the starting normal form, this is constructed, this can be efficiently done. Okay, so what's the problem? What if local neighborhoods are just as complicated as the whole graph? For example, if you have X vertex, one vertex connected to all, then the local neighborhoods are just the whole graph. So you haven't gained something really. What you need is that the local neighborhoods must be really simple. We need to understand local neighborhoods and also that one making this more is also with one can we not remove it and after that we want and keep the information stored somehow that there is additional working. So this is exactly the idea of the monitoring algorithm for knowledge graphs. We introduce again the so-called splitter game to understand, to recursively understand local neighborhoods. Suppose this game work, this is now a second definition, nowhere in this class. The first one, we cannot define everything with first-order logic when a subgraph goes class. It's now game definition. We have two players, connector and splitter. Connector wants to show that the graph is really complicated. Splitter wants to say actually it's simple and we can do one. So the players play in rounds. Connector will always choose a vertex V and say, let's go to the R neighborhood around this vertex. Let me demonstrate that this neighborhood is really complicated. And Splitter says, well, it is complicated, you are right, but let me delete one vertex. And now it becomes simple. And Splitter wins. When the graph becomes empty, then we have trivial knowledge. So we have all neighborhoods. It looks really complicated. Connector says, look at this neighborhood. This is super complicated. But it says, let me delete one vertex. I kick out this vertex. Now it is simple. Connector says, no, look at this neighborhood. It's still complicated. With the vertex, now it's complicated. So we prove that this game terminates in a round and in a round, depending only on the radius. They will always terminate after any round because we delete one vertex after the next. The limits behavior when it terminates after a number of rounds that depends only on the radius. This is the case if and only if the graph is nowhere. So this is how we monitor. We look at the local neighborhoods. We try to monitor if it's still complicated. We say, let's delete one vertex. Let's encode this deletion into our formula. We train the new formula now. But we say the neighborhood has become much simpler. We can recurse. And because we have found that recursion only, we can move efficient knowledge. The depth of the recursion captured exactly by the same. we cannot refer to the all neighborhood because we would have a branching degree of n that is complicated. And so we would have a running time of n to the L of R, where L is the number of rounds, the length of the game. We have to refer to 3 from the n of the L to the how we handle this is we grouped nearby clusters in so-called neighborhood covers. So these exist for neighborhood covers the model and drops, and by this we could have about the recursion with not such a big branching degree and do the model training. So what we can take away here is the element-based method. So first of all, load properties and understand the local elements. You take it. What do you know, for example, about planar graphs? Their neighborhoods, their local neighborhoods, even have found tree lists. Yeah, so they have very, very low. But you see the problem with the A here, with the single vertex ties everything together, we have to be what recurs with the. So this leads to efficient algorithms. If this appears in one of your problems, maybe it's usable. This is a technique here. So really distilling the technique for first order model checking for the problem is this game-based method combined with neighborhood covers. How do we lift the game to dense graph? Yeah, we're using just single vertices. This is made for sparse graphs. We try to lift this now to dense graph to get a game for more general graph classes. So that the basic technique is still there. We want to recursively decompose neighborhoods, but we want something that allows us to deal with really dense graphs. What we introduce here, this is called a flipper game. So the flip between the sets A and B complements the adjacency between the two sets. And so if you have a biting, a complete bite of the graph, you partition like this, and you flip away all the edges between the two parts. If there is one edge, then you will introduce the one edge. So the important that you use edges and not. So we can look at but then instead we use one word on the flip again, flipper will flip between the two sides. Right, see it. Right. We cannot make this last vertex disappear with a flip, but this is again a trivial base case where we can do it. So, but again, same situation. Connector says this is a complicated neighborhood, and now flipper with different neighborhoods. We will go to another neighborhood and so on. Same principle, just as vertex divisions, we can recover these flips by logic and we might taking exactly like this. So the third thing characterizes the number of the so-called genetically stable graph classes. Stability is again one of the core concepts of classical model theory. Actually, it's even more about stability than about dependence. This is one of the key dividing lines in model theory, in the very classical model theory. And we characterize now those genetically stable graph by this game. So a very combinatorial approach that works with finite graphs and that allows us to do model checking in the same recursive manner. So the game was introduced here, and it turns out so stability in classical model theory would not be defined with this coloring step that we have to here, but it turns out that in hereditary graphic, stability and monadic stability is just the same. Right? So we are really working in the right framework, as it turns out. This. So with this again, class neighborhood covers this year with efficient model checking for no-limits classes. The split again is a game where we from quantum flatness is known that was introduced by Amit Bala in 2010. And here we have a split again neighborhood covers. So this is the split again, and the neighborhood covers the two is called the these monetarily stable classes. And again, it is again, if you want proper definition, the flip again is in the form of flip level. That does the analog of this flip level. So we do monetarily all the way up to monadically stable classes. Now, super important subclass of those monadically dependent classes. Then very recently, also a new notion has been introduced, twins. Yeah, this was absolutely groundbreaking. It was introduced, here. Yes, it was introduced in 2020, so just a few years ago, and had an immense impact on structural graph theory, on algorithmic graph theory. And it turns out that also from the logical perspective, this twin decider is something very special. We have that hereditary graph of order twins. So if you add additionally linear order to your graph, and this is from the twin, if and only if first order logic cannot define all graphs from it. So again, we have this special thing, it's something special from the point of view of logic for order twins. Now, they hope that on unordered classes, you can do efficient modeling. What we need here is some additional input that we don't know yet how to compute. But if we have hereditary classes, ordered graphs, then everything can be efficiently computed and model checking is checked. So this is from 2021, and it's some indication that the conjecture may be proved. Also introduce a new, very nice width method, still generalizing widths. We are simply trying to explore this whole world of monadically NLP classes. This is one additional measure, and we can look at this figure here. So for our privilege, we have all started, we know how to do efficient modeling. If there's no order given, some additional input has to be given to effect the amount. Then generalized construction about time and privilege is on the flippers, and file on the flippers, to generalize for structure knowledge and stuff. So this is the mathematical universe of first order logic as we know it today, which is a big conjecture in the room, whether first order logic can be extracted on monadically NLP classes. And we know already that we cannot go beyond these classes, so this is the natural limit of tractability. And yeah, what are we making? We are getting game characterizations, combinatorial characterizations, the neighborhood covers really. But the rule is somehow there, but many technical details to be worked out. I want to show you something more, something very new as well. So the shortcoming of first order logic is that it can express only local. Just as we have seen, Guy from its normal form tells us we cannot even have connectivity. Because we can check only local things. We need many quantifiers to test the two vertices are connected. And so connectivity is not expressible. Whether there is a cycle is not expressible because cycles can be long. These are global properties of graphs. Feedback vertex set can be vertices such that the resulting losses are cyclic, fiber dynamics, linearity, this one path. All this cannot be formulated with first order logic, but it's very interesting properties that we care about in our algorithmic problem. We can, of course, use MS code to express them, but then we know already that we cannot go beyond bounded triggers. So we have a stronger logic that we formulate, but we have no practicability. So the classical approach is to use some recursive mechanism. For example, to consider the fixed point logic or closure logic. But these logics, the model checking problem also here is hard, essentially when we go beyond our previous one. Yeah. So testing kind of the closure logic is hard on planar graphs of maximum. So there's no hope of having nice structure theory of tractability that goes beyond periods. So we can use it manifold. Take from order logic and add some operators that can express these properties. So, for example, an operator for productivity, an operator for different types, an operator for bypass. And see, can we still do model checking with the sufficient thing? Right? So we want to connect the order. So we can express these algorithmic properties. But we must find a balance. We cannot make the logic too strong, otherwise we don't efficient model checking. So we want to find this balance here between expressiveness and efficient model checking and a rich structure theory. So on several groups, look, it's the group of around Theorems and other four logic for compound logic. That is very interesting how the people in parameterized complexity was made to express graph modification properties. You need k vertices such that something happens. And this can be very conveniently formulated with this logic. It's a very complicated logic as well, because generalized even more, there are more convenient logics now. They prove that this was expected on one class with minus. So there is now this nice interplay. We cannot go all the way to no index classes. It becomes hard in non classes with excluded topological because connectivity destroys all our locality-based methods. And we cannot use the no index approach in terms of the hard on quite quickly. So, we also introduced a logic here, separated logic. This is third order logic plus connectivity operators. And we probably look at this. This is independently introduced by Nico Janczyk. We prove that speculative classes is excluded from logic language. And we have moved something right. It turns out that the subgraph of that exclusive of a logic alignment is and only if saturated logic cannot define all graphs from function. Yeah. This is always an indication that you are looking at some good logic when the logic defines a natural well-known graph. Yeah, excluding topological minus, this is well-studied graph transfer. And the logic captures exactly this class. Yeah, so it is something good, a good definition, and the matching tractability result here. We also look at the first order constituent class. This also tractable class is excluding topological minus. In fact, we have the same tractability of classes with excluded minus as for separated. Yeah. So these logics, they sit here, excluding topological minus, and we have it. Virtual function is predicate can be tested there. We have the common logic with more logics floating around that can express different properties that we have. I want to give you an idea of how to solve the model checking problem for separated logic. So let me introduce separated logic. What do we have? We have first order logic. And then we additionally have these connectivity credits. What do I want to say? I want to say X and Y are connected after the deletion of that one to that K. Yeah, so I'm not only asking about connectivity, this would be too simple, but I want to do this modification process, feedback vertex, for example. Yeah. So after they connected, after deleting those K vertices. What can I express? For example, the graph is connected. I can just say for X or Y, I do nothing there for them. The graph is K-connected. For all K minus 1 vertices that I believe, all other vertices are still connected. This is exactly the definition of K connectivity, which I then very initially formulate with separation. I can say that it's separate. So how do I say this? I have my big cycle. I say I have three vertices of the cycle. X, Y, and Z in the middle. I say, if I delete the middle, there's still a path connecting them. And so this is how I can say that it's a cycle of the X, Y, and Z. We add X, Y, and Y, Z. Then we delete the vertex, and I still have a path. Then I can formulate the feedback vertex set form. There exist a vertices such that if I delete them, I have no cycle left. I know how to say cycle, so this is a property that I can formulate inside it. How to approach the model checking problem? It is based on a very recent and very nice decomposition theory for that, which has had a major impact in parameterized complexity for all kinds of connectivity properties. And this really captures now the essence of the problem. So separation in the graph is imperative of vertex subsets, partitioning the vertex set of the graph. And the intersection of the two sets is called a separator, and it's a separation if no edge crosses separator. So there's no edge between vertices in A without B and B without A. The all separation is the type of separator, the intersection. I call the graph QK and regular if I cannot break the graph in a balanced way. So if every separation falls in this case, one of the sides might be small. Either A has a most two vertices or B has a most two vertices. So I cannot break the graph in a balanced way if I have QK and regular. This is the standard. The graph here. My separators that some vertices to separate vertices. I cannot create many large components. I cannot break this graph with a small separator in a balanced way. So I will first one giant component and then a few very small components. At most two vertices in total. And what I'm telling now is that if I have a QK and break with the graph, then my whole separator logic collapses to plane first order. So that we apply first order mobility in to just simulate what I was saying. Okay, how is this possible? First order we can express only local properties. And now the additional combinatorial information that my graph is QK and breakable. So let's see, how can we express the two vertices S and T are connected when the demand and decay have been deleted. So I do an external search from the vertex S in the graph where the decay vertices have been deleted. And I do the search only for Q many steps. So if I have visited Q plus one vertices and I didn't find T yet, then, or I did find T, then I return that we are. But I have done only Q plus one step. Right? But I found a positive answer already. If I explored the whole component and did not find T, then I know that I'm one of the smaller components. So I can answer what? No, we are not connected. Otherwise, if I did not explore the whole component, so if I encounter more than a few vertices, strictly more than two, I conclude that I'm in one giant component. Then we start with expert search from the vertex T. I do the same thing. If after Q plus one vertices, I have explored the component, if I found S, I didn't do it before this already in the first place. So I really replace that I didn't find S, I return that we are not connected. Otherwise, I conclude that also T is a vertical component. So I get for free the information now. I have no idea about the distance, but I know that I have also defined components that are connected. So this method, I can return that the two vertices are connected by this combinatorial algorithm. This is super helpful for all kinds of connectivity properties because I don't have to test explicitly what's going on, what is the distance. I just know that I have all the components that are connected. I can apply my classical model techniques now for those unregulated graphs. Now, of course, not every graph is regulated, but it's a super nice decomposition theorem from 2019 who proved that every graph can be decomposed. So we have a tree decomposition with small separators, small adhesions, so that each of the parts, unlike the previous very small parts, we can have very large banks, very large parts, but each of the parts is QK and regular. And what we do, So we can compute something in composition efficiently, and then we can design and program the long composition on the facts we know that our separate logic connected to our order logic will be modified and design and program after stream composition. So this is a very nice theorem from how the strategy of how to express connectivity after those solutions in a very good. For this one, similar to this work, we distinguish the case that we exclude a minor. In this case, we apply some relevant vertex technique, or we don't exclude a minor. We have an even stronger connectivity property that we can route many different paths through the minor that is in this graph. Again, information that is for free. So we have this map of the universe here. This is 1 and 2. And we have explored the tractability of first order model tracking, the very nice medium theory from smart graphs, and we have the little tractability of the knowledge and graph concept. We are trying to push all the way to the conjecture that we can do efficient model tracking on monadity and two classes. For monadic second order, the foundation of the tractability is very well understood. We cannot call the only classes with boundary secrets. And then there's this new area of adding new operators that are made for algorithmic properties, connectivity, and this one part, and so on. So we can check them in many cases for classes with excluded minors based on these highly connected decompositions. Decomposition, highly connected parts where connectivity just breaks down. So thank you very much for listening to me. I hope you had a nice impression of what's going on in the mean theorem world, in the first order, monadic second order world. If there are any questions, please.
So in the games like paper or splitter, so when you are splitting, removing the vertex, let's say, so what would condition to kind of keep the small in the original graph? You have conditional formulas?
So if you remove a vertex, your formula changes, right? You have to rewrite the formula. You remove the vertex and you color the neighbors, say that, to indicate that this one is one vertex. If you want to transfer the connectivity after this, and you say either we are still connected, or we come to we are connected to a red vertex, and there is another red vertex that reaches our target, right? Because we become along the vertex, or even without if it's different, we can say that there is a connection. But we need to rewrite the formula. So the formula is more complicated, but the name of it has become simple.
So the definitions when we are saying that a class, the definition of class saying that is not expressible by, let's say, so how is this useful? So because there are multiple classes which have the same definition. So what is the useful here? How is it useful from the perspective of model checking?
So for model checking, we know that this must be the limit. Right? If we can encode everything in our class, then we cannot do efficient model checking. Because you can encode all the graphs you will get partners, because in general the problem is solved, as we know on the first slide. It's a fundamentally useful definition, right? There's nothing you can rest now. You cannot define no existence, you know. You just know I cannot define everything. What we search for really are combinatorial definitions, like with the game, with forbidden patterns, excluded minors, something like this, right? We need something that we can use from methodology. And this job is really now about for these logically defined classes. Therefore, monadic stability, monadic dependence, they are really defined in order to by first order dependent everything. And we work with combinatorial definitions and that can really work as very can do either way. Otherwise, but it might be in, but it's not very useful. It might be something like that. And now we can combinatorials.
Yes. As far as the original complexity of formulas that you consider, so you have sigma 1 and pi 1 formulas, essentially. Do you ever go beyond that or to what level? Or
So
you
next
process
or say a full second order logic or something like this.
no, just the basic.
Well, on this fantasy where we do logic, we consider full first order logic. Yeah? It is just to see that really also first order model checking defines natural complexity classes. Right? So it points in a very natural way to what people do in the complexity theory. It defines the polynomial hierarchy in space for the full model checking problem complete for P space. And then the ordination hierarchy for first order corresponds exactly to the ordination hierarchy or then the starting with a hierarchy. Was to show that it's really hard problem, and that maybe for existential formulas you get from similar model checking and some classes. This is often the first step to the existential model checking problem, but as soon as quantifier eliminations are introduced, usually we find the hard. So when you quantify elimination, it's usually about eliminating one existential quantifier, and if you can do this, your machine will slowly.
I think having a relation with that, don't you expect that you are finding neighborhood that you are doing something so that you think that the profit is just so that is having relations.
I think some of the methods have been applied in property testing. Yes. I'm not very familiar with the area, I must say. So this is usually done in low degree graphs, right? So in bounded degree or wholly log degrees. And then of course you have the strong locality-based methods as well. Because you simply have bounded size neighborhoods, and this is then often exploited. Exactly. It may be very useful to say, make my neighborhoods well behaved after some deletion. I don't know how in the property testing setting you can find the vertex efficiently that you have to do. Yeah, so maybe there needs to be some reprocessing to give you the vertices. Yeah, because by sampling you will not find them, right? Maybe this information helps already, but I don't know. So the direction for first order logic doesn't really matter. It can also test directions. Yeah, and you will have for third order logic, you have essentially the same theory of trackability for directed and undirected paths. For the separated logic, for connectivity properties, this is much more difficult. Yeah, it becomes hard very, very quickly. Directed graphs are just much more complicated there, and you don't have the nice decomposition theorems in this way. It's very interesting to see actually where you can go with directed graphs. We didn't explore this too much, Even more generally, we wanted to look at regular class queries. Yeah, so add some colors on the vertices again and ask, are vertices S and T connected by class satisfying a certain regular property? This also becomes hard very, very quickly. But it's a very good question. This is the conjecture, exactly. Sorry? So for the hardness, the hereditariness is important, exactly. And for the positive result, I would assume that we get it for all monadic unit classes. Therefore, at this point, yes. So this is ongoing work from the Warsaw group around Szymon Turunczuk, Michał Filipczuk, and so on. They characterized the monadic unit classes by excluded or forbidden patterns, which are related. So one subdivided ticks, and then it always close under flips. So these must be excluded, and they have very nice forbidden configuration characterizations of these. And by this, you get the hardness of model checking there as well. And that even existential first order logic is hard because you will be able to detect the patterns and encode everything. Thank you very much.
Thank you for your.
We will incorporate, but we will sacrifice our job rate in this story. Like 200 days in the sentence. So I'm very confident.